Um, Thank you for arranging this talk, and good evening everybody. So, though it is organized as a part of a series of sessions in Linux user group, I was told that the first talk would be much more general. So the topic is not restricted to Linux or open source. The topic is general overview of all the possible major research areas in computer science. But the goal is that perhaps some of you will be motivated in future to pursue research or projects in some of these areas, and then you can use open source technology to implement your system. So that is the idea. And I was also told that most of the audience will be from first year computer science. So I have prepared my talk according to that view. However, I believe that it will be interesting to general audience as well. So, because you are at the very beginning of your academic career, so here I will not mention in detail how to do the research. I will give a broad overview and maybe some directions, but mostly I will focus on what are the research problems and what are the application areas and how it is connected to whatever you are studying. So feel free to stop me at any point of time. So to begin with, I am quoting famous computer scientist Dijkstra, who is famous for his shortest path algorithm in graphs. For those of you who happen to know it, he says computer science is no more about computers than astronomy is about telescopes. So all of us know that astronomy is a subject that deals with the outer space, the stars, the galaxies and their configurations. Okay? But in general, it does not study how the telescope works and etc. That is a matter of optics and instrumentation, optical instrumentation. So, in that analogy, computer science is much more broader subject. It uses computer as a tool, but in reality, it has very little to do with the physical computer itself. In most of the cases, of course, there are some hardcore research focused on particular elements of the computer, and I will touch those issues also. But we should keep in mind, because in my experience, whenever, say for example, I am in the interview board of say Grand Viva or any other such forum, whenever we ask any student or say in any recruitment board that what is your favorite subject in computer science that you have studied for 4 years or say 6 years, those of for masters. And most of them answer that, okay, my favorite subject is Java or C, okay, or .NET or something like that. So then, it is like asking a student of literature that what is your favorite topic, and you expect an answer that, okay, I like history of literature, or I like novels, or I like, poetry or drama, but unexpectedly the answer comes that I like Telugu, or say I like Chinese, something like that. So it's that kind of thing. So language is just a tool to translate your ideas and thoughts into implementation. And you can actually implement any algorithm or any solution on any problem in any language. It's just a matter of more efficient or less efficient, more memory taking or less memory taking, or more time consuming or less time. That's all. Otherwise, languages are not part of computer science. So that is the point. So on the left panel, I have a broad list of contents, and inside each list, I will subdivide into several topics. Of course, the computer science is a very large domain nowadays. Okay, it is not possible to touch all the areas in a hour-long talk, but I will try to touch on the major areas. So the first subject that you learn in computer science and also in other engineering disciplines, right? In some university it is third semester, or some university it is fourth semester. I don't know whether it is taught in second semester. Data structure and algorithm. That's a very common topic. So those of you who are first year, who are entering into the engineering discipline, whether computer science or otherwise, for them, let me tell that. So when you write a code in a computer, right? When you try to solve a problem using a computer, so you have a step-by-step process, and that step-by-step process is called algorithm. So when you translate that step-by-step process or algorithm into computer understandable language, then you get a program. And in that program, you must give some inputs and you get some outputs. So basically, you have to map your problem into input in a particular format that the computer in that particular language will understand, and you will get your output. Then you have to interpret your output, map it to your real world solution. Right? Now, so the job of the program or the algorithm is to process those inputs and through that process generate the desired output. So while processing those inputs, the algorithm or the program or the system must store some data internally, must represent your inputs, and also store some intermediate variables or intermediate results. Right? That is also needed. So the format in which these data, inputs and the intermediate data that is used in the processing, that data is stored and accessed and modified and deleted and added. So the way it is done, so that particular format is called data structure because it gives a structure. So for example, an array is a structure, okay? So which is a linear data structure. You have an index A0, A1 up to say A minus 1. Okay? So this is, you can say this is a list of numbers. That is a simple example of a data structure. There are much more complicated data structures. Okay. So suppose you are dealing with three variables. Right? You want to say add three integers. Then you can define I have three in the particular programming language. You can declare three variables. Say integer A, integer B and integer C, and you want to add them, you're fine. But suppose you want to process all the marks of all the examinees of the joint entrance exam this year. So definitely you will encounter 10 lakhs of record roughly. So if you want to declare variables corresponding to that, you have to declare say integer A, integer B, integer C, then you have to consume integer Z, then you have to say integer A or A1, A2, A3. And you will go on writing. So you will be writing 10 lakhs many variables, and that is not practically feasible. So an array is something which addresses that. You can simply write say int. It may vary depending on the language. So this is in one particular language. I can write maybe say something like that. So it's 1 lakh elements you can access by A0, A1 and A. It's just an example, but you don't have to know the details. You will learn it in your data structure course anyway. And those of you who are already in their second or third year, they already know it. So this is just for the first year students who do not know the concept of data structure yet. So my point is that so array is a data structure. Similarly, we have so it's the linear data structure. So the data is accessed from one end to the other end. Okay, you can access the ith record directly. There are other data structures which are non-linear data structures. For example, you have trees. So you have a root, then you have a left branch and right branch, then you can go on. You have graphs, which are generalization of trees. You can have linked list, double linked list, circular linked list. There are many complicated data structures. And there are many variants of trees also. But all these, so when you will learn the subject of data structure, you will see that the purpose is to impose some structure. For example, here the structure is they are continuous. You can access them one by one. Okay. So if you have a tree, then there the structure is every node has a parent except the root node, and every node has two children, okay, and some of the children may be empty. So that's the regularity on the data. But nowadays, as we are progressing in the age of information technology, we are encountering some data which are inherently unstructured. So you will not encounter this in your data structure course. Probably later on, if you want to pursue some project or some research material, then you will hit it. And this unstructured data arises because we have data from various sources and in various incompatible formats. So for example, consider a social networking sites, right? So you upload your video, you upload your images, you post comment, then you chat with your friends. Now these data, they have no structure. They are of different kinds. One particular kind may have a structure of its own, but in general, if you consider the pool of the data, it can be anything, right? It can be any multimedia object, it can be any file in any format, and also the size is also not fixed. So this managing unstructured data requires special kind of data structures or data storage systems. So our conventional data structures that we study in our textbook or that you will study in your curriculum will not be helpful in that context. So that is one very flourishing research area nowadays coming up, how to handle unstructured data through intelligent data structure. It could be dynamic data structure, and it could be different kind of database as well. I will mention similar topic when I come to database. So the next in the subsection of data structure and algorithm, I have already mentioned. Okay, so as I was saying that nowadays most of the data, and here the figure is that 80 to 90% of all the usable data in all organizations are unstructured. So that is the current statistics. Fine. And the techniques that are used are data mining, natural language processing, text analytics, etc. Okay, so from data structure to algorithm. Fine. So randomized algorithm. Again, it's difficult to explain to first year students, but I will try my best. So as I mentioned, an algorithm is nothing but, you can say, a step-by-step process. Okay. So it has inputs, and then you get outputs. Is it visible in the back? Is it visible in the back? Fine. Maybe the black one is better. So anyway, so I was saying that an algorithm is nothing but a step-by-step process. So for example, say when you calculate GCD of two integers in your childhood mathematics, you follow a step-by-step process. You take the larger integer, you keep it in the middle, then you divide the larger integer by the smaller integer, you take the remainder, then you make the remainder the divisor for the next iteration, and you make the divisor in the first iteration as your dividend, right? And then you continue until you get a zero remainder. When you get a zero remainder, then the divisor in the previous step is your GCD. That's what all you follow in your school, right? One by one. So that is a step-by-step process. So that is an algorithm. Similarly, for any problem that you have to solve in computer, you will have an algorithm. Now, most of the algorithm, what to say most? In fact, in your undergraduate curriculum, all the algorithms that you will study are deterministic algorithm. So deterministic in the sense that if you give the same input to the same algorithm, no matter in which language you are implementing, no matter in which platform you are running the program, the same input will always give you the same output. Okay. Now, sometimes that is a bit of a problem. Problem in the sense, often there are problems in the real world for which we do not have efficient algorithms to solve. Okay. And sometimes it turns out that if we allow a little bit of non-determinism, a little bit of uncertainty, then we have an efficient algorithm. But it does not guarantee that we get the right solution every time, but most of the time. So for example, you may give the same input to such an algorithm, which you can call non-deterministic algorithm, or you can say randomized algorithm, because it has some internal randomness, and the output may be different every time. But the guarantee is that if you run it 100 times, 99.99% of the times you will get the correct result. So that is the guarantee. Or if it is an optimization problem, you will get very close approximation to the optimum. So I'll give you one example. So testing if a number is prime or not, all of you have done it in your school, right? So by definition, a prime number is something like 7 or say 19, etc. That means the numbers which are divisible by 1 and the number itself, and which has no other divisor. So that is prime. Composite means which has any other factor other than 1 or 10. Very easy to understand. Now, imagine that you have to write an algorithm, a step-by-step process, whose input will be a given integer and the output will be whether the integer is prime or whether it is composite. So it's a yes/no type of answer. Now, you may think that in pen and paper it's very easy to do, right? Because you will check, you will divide by all the numbers less than this number, or if you want to be more efficient, you will divide up to the number which is square root of that number. Doesn't matter. Basically, you will check all the possible factors, and then if you find that okay, there are no factors, you will declare prime or composite, and you have done it in your school. The problem is in computer science, often we encounter real world problems where we have to determine whether a number is prime or composite when the number is very huge. Very huge in the sense it needs thousands of bits to be stored. You can think of thousands of digits. So if you want to write that number, probably it will take 2 or 3 A4 pages. Now, that is very difficult to solve for the computer itself. And until recently, there were no efficient algorithm to solve that problem. And very recently, 3 Indian scientists have solved this problem. They have proposed somewhat efficient algorithm, but it is slow. So if you want a real world solution, that a real time solution, then you can allow some randomness, and the randomness is very simple. Okay? So there is a famous result which is called Fermat's theorem. I will just mention it without the proof. That if you take an integer a and if you take a prime p, okay, then a to the power p will give you a mod p. So those of you who do not know mod p is nothing but whatever you get as remainder after you divide by p. So for example, say 14 mod 6 will be 2. Because you can get some other things in the remainder. Because 14, 6 into 2, 12, 2 is the remainder, 14 minus 12. So similarly, if you raise a to the power of p, p is prime, so a is co-prime to p, a is not 1, is some integer between 1 to p. Then you will get back a. Right? Modulo p, that means you raise a to the power p, you take whatever is the value of a to the power p, that number you divide by p, you calculate the remainder, you will get a. You check, you try with any arbitrary a and p, you will see the result. Now, Fermat's theorem says that if p is prime, then this will hold. Okay? But the converse is not true. That means if this holds, then the number may or may not be prime. But the trick is that, suppose you want to check that whether p is prime or not. You generate a random integer a, call it a1. So if p is indeed prime, then you should get a1 to the power p. After you divide by p and take the remainder should be again the same as a1 modulo p. That means both a1 to the power p and a1 should have the same remainder when you divide by p. You take another random integer, say 2. you should get A2 mod and so on. So that means you do not know whether P is prime or composite, but if P is prime, then this will be true for any A. So if you try with many random numbers A and for all of them this holds, there are no exception, then you have high confidence that probably the number is prime. And the probability that your answer is correct, your confidence is correct, increases with the number of trials you do. Because if you get one exception, that means it is not true. It says if it is prime, then this will hold. So that means if it does not hold, then definitely it is not prime. So that is called a witness. So if you get some A for which it does not hold, that is called a witness for compositeness, because that decisively tells you it is composite. Now imagine a randomized algorithm where the input is a prime P. Internally I generate different random numbers A1, A2, A3 and so on, say 100 many times. If one of the numbers fail this test, then we declare the output is composite and this is correct with probability 1 every time. But if all the 100 trials are successful, then with high confidence we can say the number is prime. But as I said, it's randomized algorithm, that means same input, if you run next time, okay, you may get some other A's and you may get a wrong result, because just because it is satisfied does not mean the number is prime, because it may be satisfied for composite number also, because the converse is not. If the number is prime, then this will be satisfied. But if this is satisfied, the number may be prime, may be composite. If it is satisfied for many numbers, you hope the number is probably prime. Okay, so that is the gap that is there. But it was very fast in practice, and until recently, as I mentioned, 3 Indians, Agarwal, Goyal and Saxena, they discovered that AK's primality testing algorithm they became world famous for that. Until recently, before that algorithm, this was the standard technique similar to that. I mean, I have explained you an oversimplified version of the algorithm. The actual algorithm is a little bit more complex. There are some additional tests. But that is the main idea, that sometimes if I use randomness, then my efficiency may increase. So this is just one example that I wanted to elaborate. So of course I will not elaborate all the examples. Yeah.
So P itself is a 1000-digit number. It's up to it. So A power P will make the number too long. So will not that make the program inefficient?
No, so that's what I do not know. So the answer to that is, it's a to the power P exponentiation you can achieve very fast. So normally, this is a good question. So normally how you will calculate a to the power P? Let's say I want to calculate a to the power 17. 17 is a prime. Fine. A to the power 17, right? So normally you will multiply A times A times A dot 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 times A. So there will be 16 or 17 multiplications. How many? One multiplication will give you a square, right? So 16 multiplications will give you a to the power 7. But there is a faster algorithm. Say the first step, I have A, I multiply A times A, I get A square. Yeah. So next time I have A square, so I multiply A square with A square, I get A to the power 4. Then A to the power 4 times A to the power 4, I get A to the power 16. Now I have A, I multiply A into A to the power 16, I get A to the power 17. So I have 1, 2, 3, 4 multiplications. So basically, logarithmic of the number of digits of the size of the exponent, we can do it. So actually it is efficient. Last one? Okay, no problem. So any other question at this point of time? So anyway, let me discuss the next bullet. I do not know whether that comes in order, but that is one of the bullets. So let me explain until it comes. So another area of algorithm is called numerical algorithms. Okay. So what are numerical algorithms? Suppose I give you a very simple problem. I tell you, say x square minus 2x plus 1 equal to 0. What is the value of x? All of you have done it, class 7 or 8. 1, 1, right? So x minus 1 whole square equal to 0, x equal to 1, 1 or just 1. It's easy to solve, no problem. You can solve it exactly, both in hand and in computer. In computer you can write a program to solve it. Very good. Now, I write another equation in only one variable involving x and you try to solve it. So, say x to the power plus what is the value of x? Single variable. You have learned how to solve multi-variable equation, right? X, Y, Z. You have changed cross multiplication and you have solved for 3 variables. I am just telling you single variables.
Solve for x.
At least one is enough. So it's not easy. Okay? And sometimes a closed form solution may not exist. Mathematically there may not exist an expression which gives the value of x. But still there may be some values of x that satisfies this equation. So this type of equation sometimes arise in real world problem. Suppose you are driving, not you are driving, so you have designed an aircraft, or you may drive also, doesn't matter. So in aircraft there is autopilot mode, so the aircraft runs automatically. So it calculates, say, the headwind, the tailwind, the altitude, any distance of any nearby plane, their velocities, then what should be the acceleration or whether we should decelerate or not, what should be the angle of motion and everything. And it changes every moment. So there are a lot of differential equations that the system needs to solve, and those are solved in computer. And in those differential equations, sometimes many complicated terms come up, multiple powers of multiple variables, and often a closed form solution may not be possible. So then we have to solve it numerically. So numerical algorithm is nothing but solving something approximately without giving a closed form. So I will give a simple example how to do it. Say I keep on this side x. If I want to keep x on this side, then I have to multiply by x to the power 8. So suppose x and the whole thing definitely x to the power 8. No problem. So this whole thing I have written it arbitrarily. So let's call it, say, g of x or f of x, something like that. So my equation becomes x equal to g of x. Right? So I have to find an x such that x is equal to g of x. So what to do? You pick a random x that may or may not be the value, right? So you choose a random x. So you take, say, x equal to x naught, suppose. X naught is your choice. So you have chosen x naught randomly, you put inside g of x naught, you will get a value because it is an expression. If you substitute something, you will get some value. And you will check whether it is really equal to x naught. If it is equal, you are lucky. Most probably will not be in the first time. So you will update your guess. And the gap between x and gx will tell you how to update, in which direction, whether to increase the value or to decrease the value. And then you try with the next case. So this x naught you will modify to x1 depending on the gap between x naught and gx naught. You will get x1, then you will plug in g of x1. You will check the gap. And mathematically we can prove that if this function gx satisfies certain conditions, which you can check from gx easily, then the solution is guaranteed. And the sequence of guesses x0, x1, x2 will slowly converge towards the actual root. So that is just one simple example of numerical algorithms. Probably that is there in the last unit anyway. So time is short. I don't have time to explain everything in detail. Just trying to motivate the different areas.
So just one question.
Yeah.
What is the difference between an actual computer program and an algorithm?
As I said, an algorithm is a recipe, okay, a step-by-step procedure which you can write in any format. For example, for the GCD, you can write step 1, divide the larger integer by the smaller integer. Step 2, take the remainder, make it the next divisor. Step 3, continue the process. You can write in English or in any language.
Computer doesn't understand algorithm.
Computer does not understand algorithm. See, the computer, ultimately the computer is a machine. It's a hardware. There is circuit. So the circuits will understand your electrical impulses, zeros and ones, and it will interpret that. So ultimately you have to map your algorithm into something which is understandable. So for every standard programming language, you have a compiler inside which will translate the high-level language into an intermediate language which is called assembly level language, and then you have something called assembler or linker which will translate that low-level language into the binary program 0, 1, which will ultimately run in your computer as plus and minus impulses, electrical impulses. So yes, so an algorithm could be understandable by a computer if you write an interface. That interface will take that algorithm. You will say that I will write my algorithm in Bengali or in English. Say, you write an interface. That interface will take the algorithm and translate into one of the languages understandable by any one of the computers. Then it will run. So anything can be run in computer. So you just need the proper interface. So the next, I will not go into detail. There are many other exciting areas coming up. So approximation algorithm, again, it is the motivation is similar to randomized algorithm, but in randomized algorithm, the main target is the time complexity. That means the time it takes by the deterministic solutions takes such a long time. You don't want to wait for such a long time because we'll lose real-time constraint. So for example, say the aircraft, right? If you want to solve something, you have to decide what should be my acceleration in the next moment in the aircraft. If you are delayed, then your plane may crash. So we say those systems are real-time systems because you need answer right away. Okay, even if it is approximate, you don't need the exact answer. So for real-time systems, we need fast solution, really fast, in terms of nanoseconds or even less than that. So randomized algorithms are a way to achieve this. So similarly, approximation algorithm is another way to achieve this. Difference is in randomized algorithm, you have some internal randomness. Like I gave an example, you pick some numbers randomly. Whereas in approximation algorithm, there is no internal randomness in general. Sometimes you may have a randomized approximation algorithm. That is much more complicated. But in general, the philosophy is, I will want only an approximate solution. I don't want the exact solution. And the approximate solution is often faster. So that is the idea. And it's a huge subject, a huge research topic on its own nowadays. It has been developed since last few years. Another topic is combinatorial search. Now that kind of search problem arises, say for example, when you want to design automated games. Say you want to design a system that will play chess automatically. Okay. So against human. There are systems that are already built on that. So what you have to do, so you have to think yourself as a machine and you have to guess your opponent's moves, right? So you can draw the whole game in the form of a game tree. So at any point of time, suppose these are your possible options. So you know the current situation of the board, chess board. So this is your option 1, this is your option 2, option 3 and option 4. Right? And you want to decide which option to choose. But then you have to look ahead that if I choose option 1, then what could my opponent choose? Right? So this is my option. So I say this is your option, and this is the opponent option. Say O1, O2, and so on. But then you do not know what option the opponent will choose. So corresponding to each of them, again you have to think of your possible options, and so on. And of course, you cannot, in normal brain you cannot trace even 4 or 5 iterations. In computer you can trace many iterations, right? And the more efficient is your algorithm, the more depth you can track in less amount of time, and the better will be your result. Because at some point of time you have to prune the tree, you have to chop it off, and there you have to say, okay, approximately here I have this much probability of winning in this configuration, because these are nothing but your configuration, because you have a current configuration of the board. If you take this option, you get a new configuration. If you take this option, you get a new configuration. Corresponding to your one of the options, your opponent can take any one of the option, and if you follow one of the paths, here also you will get one of the configuration, right? And any chess player, by looking at the current configuration of the board, will have some idea that okay, these are the odds. This player may win with this probability, this player may win with this probability. So the more depth you can follow, the structure of the board will be closer to the end of the game, and you can guess more accurately whether it will lead to win or loss, and your guess will be better. So there are algorithms. So combinatorial search is a huge topic. Just one potential application is designing games. Such type of game is called minimax game tree, because it's a kind of, you are trying to minimize the maximum gain of the opponent, or maximize the minimum gain of yourself. So the common thing is accuracy and efficiency. Fine. So high performance computer architecture, nothing to explain in detail. So computer architecture is nothing but arrangement of different subsystems in the computer hardware. So you have a processor, you have a memory, you have a data bus that will communicate between the processor and the memory. Okay. So those subsystems, each subsystem will have a different speed. So when the computer hardware is talking to itself in its own electrical language, you need it to be as fast as possible, right? And there are applications in the world which needs fast solutions. So not only your software or your algorithm have to be efficient, right? But the system on which the algorithm will run will have to be efficient. So both together will go hand in hand. So you need high performance computer architecture for that. Then the next area in computer hardware is the embedded systems. So embedded systems means that in a small system, you actually include the power of a whole computer, right? So whatever is the power of a desktop, almost the same flexibility, same functionality you give to dedicated systems, and make it really small, right? For example, nowadays we have embedded systems, that means a processor, memory, chip, the whole computer system together embedded in MP3 player or traffic light, or in any modern vehicle, even satellite spacecraft. So everything is smart. You will hear something as smart system, right, or intelligent system. There is nothing smart or nothing intelligent, believe me, okay? You talk to the people who design those systems, these are just actuators to respond to the environment, sensors to get signals from the environment and process something internally with embedded system. In most of the cases, there is no AI in those systems. Next, parallel and distributed system. So if you are now from single computer, if you want to move multiple computers, right? You want to interconnect them together. You want to divide a problem into multiple sub-problems and solve those sub-problems, and then combine the sub-solutions to generate the total solution, so that it can be faster, right? For example, matrix multiplication. If you are multiplying, say, 1 lakh cross 1 lakh size matrices, then it will take a lot of time. But because matrix multiplication, you can actually split the rows and columns, because the first entry of the product will be the product of the first row and the first column of the two matrices. Right? So ijth entry of the product will be the ith row and the jth column. So individual rows and individual columns you can throw it into different systems and you can do them parallelly and then get the result of the product in parallel. So that's just an example to motivate. In parallel distributed system, the research is more challenging than individual system because you need synchronization between the system, okay, and correctness. Then there are different categories of processors. So the normal CPU that we see in the computer, that is a general purpose processor, because you can write an algorithm for any problem, it will solve it. You have ASIC, that is application specific integrated circuit. So that means you build a computer system to solve a problem in a particular domain. For example, you have ASIC, say, for medical instrument. You have ASIC for ships, etc. Then ASIC, application specific instruction set processor, that is an intermediate between your ASIC and general purpose processor. Your general purpose processor is big and flexible. Your ASIC is small and dedicated to a particular problem. And ASIC is something in between. So it has the miniatureness of ASIC, but it has the flexibility somewhat of the general purpose processor. So these are coming up nowadays. Then there is GPU. You will all hear NVIDIA GPU and stuff like that, graphics processing unit. So basically, if you have any kind of data structure, for example, images or videos, where you have numbers arranged in the form of a matrix, those kind of computations are pretty fast in this graphics processor unit. So these are special systems. Then DSP is digital signal processing. So there are special chips, boards available for digital signal processing. There, basically you take input as an analog signal, you convert it into digital format, and then you apply some algorithm on that digital signal, process it, and then maybe map the output again to the analog domain. I'll give some examples later in some other applications. So the next item in hardware. Okay, do I have time? Half an hour more is fine, right? I started roughly around 6, so I'll try to finish by 7 o'clock, okay? Fine. So in computer hardware, you have the next area which is called VLSI design, and the name says it is very large scale integrated system. So now, so far we discussed with small system dedicated to achieving a particular task. Now you have a very large system, but you want to force everything on a small chip. Okay. So that is VLSI. And an advanced version of VLSI. VLSI is there since last say 20-30 years. But it has been scaled up to such an extent. I mean the functionality has been scaled up and the area of the chip has been scaled down to such an extent that we need a different subject which is called system on a chip, because you now have the whole system on a chip. In VLSI, typically sometimes you have only one component in one chip. But in system on a chip, you have all the components in a single chip. Okay? So it's not a board where you have put multiple chips together and they are functioning. You may have an embedded system where you can have a card. Okay? In that card there is a slot for a CPU, a slot for a memory, a slot for something. Power management. So that is an embedded system. And if you miniaturize it, make it more efficient, you can have a VLSI system on that. But when you have a system on chip, then all these different subsystems, instead of they being different chips, they will become a single chip. Okay? So that is system on a chip. The next level is network on a chip, because now you have single chips embedded into different computers and you want to communicate them through networks, normal networks. And here the goal is to simulate the entire network on a single chip, so that you even miniaturize the whole thing. So that is an upcoming area. And the next area that has very recently come up is called lab on a chip. So there you can put an entire laboratory inside a chip, and this area finds particular applications in chemical analysis, or say environmental monitoring, medical diagnosis. For example, you might have seen there are some devices to measure your blood sugar, right? Instantly. So you get a stick like of a thing. You take the blood and you have to put one drop of blood onto that stick, right? And actually there are circuits. There your blood drops is being divided as microfluids, and the fluid is going into the networks. Some computation is going on, then it's giving you the result. That's a very crude and small example, but you can achieve much more complicated tasks. Okay, so the picture tells you everything. Okay. So instead of doing the actual experiment, the chip will tell you the output. Okay, so you can search in Google, you'll get more. So I'm done with hardware. So the next is system level stuff. So in system, I have operating system, I have network system and other thing. So under the section system and under the subsection operating system, there are many areas like kernel optimization. So kernel is nothing. So okay, so operating system is what? For those of you who are in the first year, operating system is again an interface. As I was telling you, in order to communicate with the computer, you need interface at every level, right? So just writing your program is not enough. So you need an interface which will act between your program and the environment, the hardware in the computer. So operating system is such a thing. And in the operating system again there are different layers. So the innermost layer is called kernel, which actually talks between the upper layer of the operating system, say the user layer, and the hardware or the device drivers. So this kernel, you can, for now, you can think of it as an interface between the, say, the user level system and the internal hardware to make it simple. Okay. So there are many research areas how to optimize it, how to efficiently communicate between these two worlds, how to efficiently connect, how to send the input from one world to the other world and vice versa, much more efficiently with synchronization, without error, etc., etc., etc. Multi-core system means there are multiple CPUs combined into one system. All of you know, quad core system, 8-core system, then 16 core, 32 cores. So again, there are scheduling problems. So you want to schedule your task. So which core gets what part of your task, right? That kind of stuff. Then the synchronization between them, that becomes a very prominent issue in the system research. Then real-time operating system, RTOS. I already gave some example of real-time operating system. Okay, that is used in mission-critical applications like aircraft or defense applications and stuff like that. Then nowadays we have mobile operating system. So an entire operating system is the same thing. In the computer you have an operating system that acts as an interface between the user and the hardware. In mobile also you have the operating system. That's why you have so much features that you did not have in earlier phones. So mobile phone is becoming more and more closer to a computer because it has a whole operating system. And examples of such operating systems are iOS by Apple, Android, Windows 7, BlackBerry, etc. etc. So, computer networks. So, mobile networking nowadays is coming up. Traditionally, we had typical computer networking. Okay, so you have one computer situated here, another computer situated there, thrown in a room. You have a structure, then you have to connect them through cables and links. Next, you had wireless systems, so where you have to make arrangements so that two devices who never communicated to one another come in a proximity and then they start talking to each other. So wireless communication, that is another topic of research. And there, how do you avoid confusion? Because one device should not be able to garble the two signals from two other devices. Okay? So you need to separate the frequencies and there are different issues. There is energy aware networking. So in networking, people often talked about how to communicate from say point A to point B as fast as possible. So suppose point A is a computer in Calcutta and point B is one computer in Los Angeles. You want to communicate between the two. So from computer A, it goes to the local say internet service provider or to your modem. Through modem, it goes to the internet service provider. Through them, it goes to the satellite. Through satellite, say it goes to the local server, the internet service provider there, and then to the local modem and to the local server and the local computer. There are so many hops, right? And there could be multiple options in this path. So what is the most efficient path in terms of time and cost? That was the traditional area of research in classical networking. Nowadays we have energy aware networking. That means we are not only concerned about how fast we can send them or in how much less cost we can send them. We are also concerned about saving our energy, because our devices are becoming smaller and smaller. They are like, for example, we are having RFID devices, we are having sensor devices which run typically on battery system, which do not have any constant power source. So there, if I want to make them communicate with each other, okay, while being situated in different parts of the world, so I need a networking which may not be fastest, but may be fast somewhat, but with least energy, right? So I have multi-objective optimizations. I have to optimize the route length, the route cost, and the power or energy I am consuming. So you have to take into account what was the initial energy of each of the subsystems. What is the rate of energy dissipation of each of the subsystems? Okay? What is the antenna property of each of the subsystems? There are huge issues coming in that. So data center networking is nothing but where you have heterogeneous systems, particularly in cloud networking. You have heterogeneous components talking to each other, and they actually talk through several data centers. So that is data center networking. Then the vehicular networking is a picture there. So basically it is used in intelligent transportation. So you have multiple vehicles and they communicate with each other. So this is nothing but an extension of a mobile ad hoc networking, because these are mobile vehicles. So you want to track, say a company want to track that where the vehicle is going. Okay? If the item is being delivered to the proper distributor in due course of time, you want to get automatic SMS that your item is delivered. So that kind of stuff. So database management system. So that is another system under the system category. So database is nothing but an organized way to store data in the form of a table. So sometimes in your attendance register you make tables, right? Name and the signature. Or when you have to arrange a big program, you make tables. What are the items, what are the cost, where from to buy them, what is the rate, who will buy them, by which date it has to be acquired, many such things. If I want to keep details of a department, then what is the department ID, what is the student ID, what is the roll number, what is the subject, etc., etc., etc. So you arrange your data in the form of tables, and how these tables will be organized, how they will be stored, how you will retrieve a data from single table, from multiple table, how you will combine the data, that kind of stuff is there in database management system, which you will learn in your course in due time. Distributed database is a lift of that traditional system, where you keep a same table, a single table, you split it into multiple sub-tables and you keep them in different databases, located in different locations. Right? So then if you have to retrieve a data, you may have to combine them through networking. So that's how the issues come into play in distributed database. So how to divide your tables, when to divide your table, how to process the query. So a user is wanting some query. Okay, I want the list of, say, employees of this organization who have drawn their salary between this date to that date, something like that. So I need to process the data from the tables. So if the table is distributed, then I need to follow specific algorithms for distributed database retrieval. So that is one important aspect. Then query optimization. So same query that is used to retrieve some data can be executed internally by the database by multiple ways. So for example, say I want so all the students from non-computer science department who are in second year, right? So I can calculate who are the second year students first, and then find out of them who are from non-computer science. Or first I can find out who are non-computer science students, and from that I can decide who are the second year, right? So I can process the same query in two ways. Agreed or not? Right? Two different ways. This is just a simple example, but in a complex query, there may be multiple options. There may be 10 different ways of solving a query in 10 different orders. Now, which one of them will be faster? That is the topic of query optimization. So, your database system gets a user query, it has to report some result, but before doing it, it will do query optimization. It will decide the sequence of operations, the optimized sequence of operations, so that the task will be simplified and it will be done in less amount of time. That is query optimization. Then there is data obfuscation. That is very important in terms of medical data. Say for example, so where you want to give access to some part of the data, but not every part of the data. Say for example, you don't, say in banking survey, you don't want to reveal your salary. Maybe in hospitals, hospital records, if they give your data to some organization, you want your name to be suppressed, name and identity. They may send your disease, your blood pressure, your blood sugar, but anonymously, you don't care. So that kind of technique where you have the whole data available, but depending on who is the user, depending on who is processing it, when it is being processed, you will give access to particular field of the data. That is called data obfuscation. And sometimes there are ways which you can store the data in an obfuscated manner. Then nowadays this big data is coming up. This is again related to the unstructured data structure that I mentioned in the very beginning. So, for example, you can see the volume of the big data. Every 60 seconds we have 98,000 tweets, 6,95,000 Facebook status updates, 11 million instant messages, 6,98,445 Google searches, 160 million emails sent, and 1,820 terabyte of data created, and 217 new mobile web users. Okay, and this is an old record. I believe now it is even much more. So the whole internet system, okay, or the cloud has to maintain such a data, process such a data, ensure correctness of such a data in an efficient manner. So that's a huge task. So there are many technologies coming up. Many of you have heard the name Hadoop. That is one such technology to process big data across multiple heterogeneous systems. Okay, next I am towards the end of the talk. Relatively closer to the end of the talk. Not here, across the middle. Okay. So spatial data processing. So spatial data processing means data related to space. Arrangement is space. So these are not related to time in general. So of course, if you think of the video, you can think of it as temporal data also. But essentially, a video is nothing but screenshots taken, say, every millisecond. So it depends on whether you are taking 30 frames per second or 15 frames per second. So video also can be thought of as images, and then your data is spatial, not temporal, not a function of time. So anyway, so in computer graphics, again you will learn in computer graphics so how to represent the different shapes, different structure. Given a structure, how to modify the structure by mathematical operations. All that you will learn in computer graphics anyway. But these are some advanced topics which probably you will learn some of each in your master's level course, or maybe during your research if you choose to do so. So animation and game design is an advanced area of computer graphics. It requires a lot of effort. Then computer vision and image processing, I am just giving some example. So scene reconstruction, object tracking, motion estimation. So scene reconstruction means, so often you will see that in a playground or in a show, there are multiple cameras, right? Recording from different angles. So often, sometimes an event is so important that you are not getting the full view from one camera. So you have to combine the videos or the images from multiple cameras from different locations. So that is called scene reconstruction. So you have partial scenes from different cameras, now you have to reconstruct it. It also happens for satellite image also. So you may have different satellites, okay, capturing image of an object in the sky from different angles, but you want to now estimate the exact shape and structure of the object. So there are also such things are necessary. Okay, object tracking, an example is given here. So basically, if you have multiple objects, no problem.
Is the 3D camera which is being recently used, is it a sort of scene reconstruction?
Not necessarily, because even in 3D camera, you will have some idea about the depth, right? About the depth of the image. But that is also from one particular direction, not from all possible directions. So in 3D also we have the reconstruction problem in real world applications. Good question. So object tracking. So when there are multiple objects in one image and you want to identify specific object of your interest, that is called object tracking. So that is an advanced application of computer graphics. So for example, in traffic signal, there are automated cameras that records that say which car has crossed the speed limit or which car violated the traffic light. So from there, so probably the police department will want the number plate of the car. So there the object is the number plate. So here we see the cycle and etc. So again, so the number plate may be distorted, maybe the camera took it in a different way, maybe the car was in a different angle. So how to process it? So different images, all the images will not have the number plate in the same size, in the same shape, in the same angle and the direction, right? It may have in different ways. So we want automatic recognition of that object using algorithms of computer graphics. So that is another very hot area. Motion estimation. So that means by getting still images of a moving object at different times, how do you estimate the motion? What path it took, what was the speed, etc. Okay. Then virtual reality, I don't have to explain. So many of you have seen 3D cinemas, right, with different specs. Okay. So that is a crude example of virtual reality. I don't know if you have experienced a real virtual reality system. Okay. So it is an advanced version of those 3D movies you can think of, where you can feel that you are walking through some place. On your both sides there are different objects, maybe buildings or cars, maybe forest, but actually it is not present. They are all created by computer simulation. So fractals, that is another interesting advanced area of computer graphics. Okay, so it turns out that sometimes you can write equations. Okay? Say equations, say y equal to fx, something like that. Say y equals to fx, or more generally, say x. Let's say like this, say y, so x n plus 1 say equal to f of xn yn, and say y n plus 1 equal to say f of so g of xn y. Just as an example. So this xn and yn are your current point, say on the computer screen. Imagine. So you imagine a coordinate system, so this is 0, 0. Actually in computer graphics the top left corner is 0, 0. But doesn't matter. For your understanding, assume this is 0, 0. Okay? So this is x, this is y. You have a point which is say xn and yn. Okay? So the next point is xn plus 1, yn plus 1, and this is recursive. So you can plug in again xn plus 1, yn plus 1 here to generate the next point xn plus 2, yn plus 2, right? So from this point you get another point, from that you get another point, and so on. And often it turns out that there exist certain functions f and g such that these points, when you connect them together, they become interesting shapes. Okay? And these are called fractals. So many of you have seen fractals probably as an example of screensavers. So you will see a lot of interesting, beautiful patterns emerging, right? Same patterns becoming bigger and bigger, and again smaller patterns of the same shape are coming out, right? And what is surprising is that sometimes we get particular functions for which no matter you start with an arbitrary point, it does not matter what is your initial point, ultimately when you trace these two functions and plot the whole object, you get a natural shape. Okay? So you get, for example, tree leaves, you get mountains, you get different animals and objects and this is just some simple equations. So that is called fractals, and it has many applications. So sometimes you can transform your normal signal into a fractal signal and see something, some pattern that is present in the signal. That's not possible to see. And another implication of this is that how to model real world object in terms of mathematical equations. So one school of scientists believe that different type of choice of functions giving rise to different shapes that we see in the nature. That means for any shape in the nature, it is possible to design the functions. Maybe we do not know for every shape, but it is possible. And so that proves that everything is mathematical in nature. So we may see 10 lakh different trees of the same species in the same forest, but each of them is specified by similar equation, just one change of parameter. Okay, and they are precisely defined. So some scientists believe that is one evidence that nature or God is a mathematician. Okay. Computational geometry is another interesting area of spatial data processing. So range searching example is geographic information system. So that means you are in a particular area and you want to locate certain objects within a certain distance from your current position. So you need specific algorithms for that. You need to acquire data from geographic information acquisition system, say from GPS or otherwise, and then process that data. So we need spatial algorithms. Okay. So convex hull is nothing but if you have a set of points, say you have a set of points, something like this, thrown into space, okay? What is the minimal convex shape that covers all the points? Okay? So this is used, if I want to just draw the outline of these points, then it is a concave shape. Right? So what is the minimum convex coverage? That is called convex hull, informal. Now that is, so for that you need an algorithm. So your input is the coordinates of these points in space and the output is the coordinates of the boundary of the convex. Okay. So we need an algorithm, we need to process them. Okay, so one example is animals' home range. So often, say the forest department collects data, say the footprints of the animals in a forest, and suppose you get footprints in a particular region, and from the footprints of different animals you want to find out what is the range of travel by that particular animal, and that is given by the convex hull. Because if an animal has given in this direction and in this direction, and we are not finding the footprint because maybe it is erased by rain or somewhat, so probability is that of course that animal has also traveled in this region. Okay. So that is a natural case. So the convex hull actually formalizes that notion. So that is one practical application. Then another application is a Voronoi diagram that is used in wireless network. So that is this kind of diagram. The idea is very simple. You are given an arbitrary set of points in space located in different mutual distances from one another. So this is an arbitrary set of points. You have to draw regions around each point, okay, such that, so you can draw regions with each point in many ways. The objective is to draw these regions in such a way, one region covering one point, such that if you take any region and if you take any point inside this region, right, the closest of the given points of this point will be the point inside the region. If I am here, then my closest point would be this point, because this region belongs to this point. But if I am here, my closest point will be here. So for any point within the region, the closest point of the given points would be the point defining the region. And you know that because these initial points are arbitrary, these shapes are quite arbitrary. Okay? The shapes can be anything. So this is a very interesting problem in computational geometry, and that is used in where you should put your base station in the wireless networks, that kind of decisions. So if you have an area and if you divide the area into using Voronoi diagrams, then you try to place a wireless base station, say, at the center point of that Voronoi, so that you get the optimum coverage. So that is one example. Tilings is another area. I am not going into details. So everybody knows what is tiling. So you have given an area and you are given a small shape which can be arbitrary, maybe pentagon or maybe a weird shape. You have to fill this area with this small shape, but you have to fill as much open space as possible. So you have to keep the minimum open space, minimum uncovered space. So that is called tiling. In what arrangement you have to do it. That is an active area in computational geometry. This is a picture of Roger Penrose, the PhD supervisor of Stephen Hawking. He is a mathematician, and these tilings are called Penrose tilings. So he is one of the discoverer of a specific type of tiling. So this is just an image of that guy. Okay. So another interesting problem is art gallery problem. This is a very practical problem. Suppose you have a museum. Okay. You are the owner of a museum and you want to employ security guards at night so that nobody steals the important, most expensive stuffs of the museum. Now the museum could be in different shape. So maybe there are pillars. Okay, maybe there are walls internal. Right? So all regions are not visible from all other regions. So your goal as the owner of the museum is to place minimum number of security guards because you want to minimize your cost. But you want to place the security guards in areas such that all of them together, their vision of sight covers every point that is accessible in the museum. So a solution is given here. So you place one stuff here, one stuff here, one stuff here, and one stuff here. That is enough. So you can, basically your line of sight is a straight line. So you draw straight lines from here and you will see that you can cover all the position. And it's a difficult problem because these internal shapes and walls and obstacles may be arbitrary. That is an input to the problem. So that is an interesting problem called art gallery problem. Okay. Fine. Next. So I'm in the next topic, artificial intelligence. Again, it is a huge topic. I will discuss only specific subtopics of artificial intelligence. Okay. So one particular subtopic is machine learning and pattern recognition. The idea is very simple. So you have mixed objects. You want to classify. So this is a classification problem. What are the objects that belonging to class 1 and what are the objects belonging to class 2? So the idea is that you have to draw a separating line. This separating line is called a model. Okay. So what could be this data? So for example, this data could be a disease data. Maybe in the x-axis, I will plot, say, blood pressure. Maybe in the y-axis, say, I will plot blood sugar. Okay. Then I am looking for a particular disease. The percents, say, if with this blood pressure and this blood sugar, if someone has the disease, I mark that coordinate as a red dot. If with some other combination of blood sugar and pressure, someone does not have the disease, I mark with the green dot. And from, say, 10 years of hospital records, I generate these data, I place them red and green. Now my point is to fit a curve that separates these two data. Then I can forget all the 10 years of records, I can remember only the curve. Because now this curve defines that okay, this side I have disease, I have no disease. So in future, if I get a new patient and I monitor the blood sugar and blood pressure of that patient, I can just plot that patient and just see on which side of the curve that new point lies, I can decide what is the disease. So I can forget. So the whole game of the classification problem in machine learning or pattern recognition boils down to summarizing a huge amount of what is called training data, that means past data for which the class is known, summarizing that into a simple model. So this line is called a model. and this is a two-dimensional data, right? So I have a curve to separate them. Now instead of blood sugar and blood pressure, I may have other parameters. I may have temperature, I may have, say, whether a particular X-ray reveals something or not, whether some other blood test the value was between this range or not. So ultimately my data may be 100-dimensional. So I cannot plot it in a picture, but I can store it in a computer. Okay? So hypothetically, these points lie in a 100-dimensional space. And I need a 100-dimensional hyperplane, which is an extension of surface, 3D surface, that actually separates these two regions in the hypothetical higher dimension. So that becomes a challenging problem. And there are different algorithms in machine learning to actually find out this hypersurface. So in 2D, the hypersurface is just any curve. So there is decision tree, there is artificial neural network, there is support vector machine, reinforcement algorithm, genetic algorithm, blah 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 blah. There are many different ways to build this model. Okay. Okay, and the application is, say for example, disease recognition. That is one example. It could be handwritten character recognition. So for example, one person writes 6 this way, another person writes 6 this way, another person writes 6 this way. You want to identify or classify whether it's 6 or not, right? So you have 10 different class, 0 to 9, 10 different digits. So you will divide your regions into 10 different sub-regions. One of them you will identify as 0, one of them as 1. So your model is nothing but this partition of the region into 10 sub-regions from the given training data. Right? So that is handwritten character recognition. So that is used actually in US postal system. In our postal system, even now, if you go to GPO, you will see that the employees actually are throwing all the letters from a big bag from one region, and then they are looking manually, looking the postcode, and then they are distributing in different regions, right? Depending on the destination. In United States, for many years, this is now automated. So the first level of segregation of the letters based on the destination postcode is done by automatic character recognition on the postcode by a scanner. Okay, so that is much more efficient. Of course, in our country also these things are coming up. Okay. So that is another example. We can have speech recognition, right? So we can have information retrieval natural language processing. That means, say maybe you will speak in your own natural language, that will be automatically translated to other language. Okay? So Google Translator is already doing it in written form. It could be done in verbal form also. So that is speech processing. It's spam detection. Okay, so you can classify whether it's spam or not spam. So any sort of classification can be done. Data mining is again an allied topic of this machine learning or pattern recognition. So apart from classification and prediction, so classification means finding that line. And prediction means given a new point, where does it belong, this side or that side. So that are particularly part of data mining as well. There is another topic in data mining, sometimes it is taught in machine learning or pattern recognition also. These are all interdisciplinary topics. That is called clustering. So clustering is for which the class level is not known. So for example, in the disease data, you know which coordinates are having the disease, which coordinates are not having the disease. Okay? Or which coordinates are 6, which coordinates are 4 and 5. So you know some examples. From those examples, you are now creating your subregions and forgetting those examples. But here, the name of the example is not known. So for example, so you do not know what are the meaning of these classes. You do not know. You just have the points arbitrarily, and you do not know how many different classes are there. There will be 2 classes, 3 classes. But your objective is to group them, group similar objects together. So that is called clustering. So this is one cluster, this is another cluster, this is another cluster. And there are many clustering algorithms. So the input to the algorithm is arbitrary data points in space, maybe 2D, maybe 3D, maybe 100-dimensional. And the output is how many clusters and what are the individual clusters. That means for every point, which cluster does it belong to? NASA uses this clustering technique to actually cluster different galaxies. Okay, so when you have galaxy image, you do not know that which star belongs to which galaxy. You have a huge picture lots of points representing lots of stars. When you run the clustering algorithm on it, the output will be similar stars or physically closer stars together in one region, and you call them, this is perhaps one galaxy or one solar system. That is one solar system. So that is used in astronomical object classification. That is one example. There are many other practical applications which I have not mentioned. Association rule mining is another target of data mining, which is again very practical, real life oriented research. So it is, for example, this is also called the market basket analysis. So suppose any food mart or any mall wants to identify that, so they are observing the purchase patterns of the customers, and they are observing the customers who buy item 1 is also buying item 2 together. So that means item 1 has an association with item 2. So what they will try to do next time when they arrange their items internally in the mall, they will put item 1 and 2 close to each other in 2 closed racks, because then that will cause more sale, right? So from the data of the past purchases, identifying if there is any association between purchase patterns of the customers, and depending on that, you try to arrange them to increase your sale. That is called market basket analysis, and based on association rule mining, and there are specific algorithms that are developed for that, and that are used in practice nowadays. Then there is anomaly detection. The idea is again very simple. You have a set of objects. Suppose one object lies here, so that is an anomaly. So that's essentially example. So artificial intelligence is done. Then the cryptography and security. Don't worry, I will have only pictures, no equations. So in cryptography there are many problems. One problem is confidentiality. Confidentiality deals with, I have a sender and a receiver. They want to communicate with each other, but any third party looking at the data will have no meaning out of the data. That is called confidentiality. So that can be achieved by some mathematical algorithms that will modify the data from the sender, prepare it in a different form and send it to the receiver, where the receiver will only understand because they share a common key or a password, something like that. So that is called confidentiality. Another target of cryptography is to ensure data integrity. So that means here I am not concerned about confidentiality. I don't want to encrypt the data, but I want to ensure whatever was sent from this side is received by the receiver on this side. It is not changed in the middle. I may want both confidentiality and integrity, but these two are different topics of research, and different functionalities are needed. So I may impose integrity functionality on top of confidentiality. So you can think in terms of layers or wrappers. So these are achieved by typically error correcting codes. Those of you know it, and similar ideas. Sometimes hash functions and stuff like that. Parity bits and stuff like that. So anyway, another object is authentication. That means before I start communicating, so confidentiality is one object, integrity is one object, another object is authentication. Before I start communicating, I want to be sure that I am talking. So Bob wants to be sure Bob is talking to Alice, and Alice wants to be sure she is talking to Bob. It is not she is talking to Oscar, and Oscar is claiming Oscar is Bob, and she is saying things related to Bob. That could happen. It's called man in the middle attack. And there are practical attacks on it. There are schemes to prevent such an attack and stuff like that. So that is called authentication. We do it in our real life also, right? So if a police officer comes to arrest you, you will say that show me your ID. Even the ID also can be fake. So in cryptography also we have that. Okay, so where am I towards the end? Interdisciplinary areas. So these are actually most exciting. When I was preparing these slides, so for me it was most exciting, these interdisciplinary areas. For example, robotics is an interdisciplinary area because it requires mechanical engineering to build the arms and legs of the robot, to have their movements. Also, I should have listed orthopedics. because you have to simulate human behavior. Electrical engineering, electronics engineering, to build the circuitry inside. Control engineering, because the robot will get data from sensors about the outside world, and accordingly its motion has to be controlled. So we need a feedback control system. So if the robot encounters an obstacle, the feedback control should instruct the robot to turn on another direction. And computer science and mathematics, obviously. This is a robot by Honda. Okay, Asimo. I have seen this robot dancing in Tokyo. You can see YouTube videos where this robot is playing music, instructing as a music composer to humans who are playing music. So anyway, this is a pretty much advanced robot. And nowadays there are, not nowadays, I think since last 15 years or more, this RoboCup soccer is being played, World Cup football for robots, where many universities participate from all over the world. And they have a team, each university has a team of robots, okay, playing one-on-one game on an artificial field, and then there are wins and losses and champions. Next interdisciplinary area is bioinformatics. Okay, so bioinformatics deals with applying computer algorithms to analyze, to understand, say the protein sequence, nucleic acid sequence, the peptide. And see, these are interdisciplinary because whatever we have discussed earlier, say pattern recognition or machine learning, could be applied here. So for example, suppose you want to identify that nowadays we know that the cancer is caused by certain deformation in the gene. So you want to identify that which part of the gene got deformed, which caused you to have cancer. So that can, so gene is nothing but a sequence of adenine, guanine, cytosine and thymine, ATGC, right? So you can write the whole DNA structure and then you can identify using pattern recognition algorithm if there is any defect. And if there is any defect, you can try to use gene therapy to correct it. Okay? So that is the application of bioinformatics, application of computer science. So ultimately it becomes some symbols. So the whole DNA is nothing but a symbol over 4-letter alphabet, ATGC. Okay? Then you can study interactions, that okay, which protein will interact with which protein. For example, this can be used in drug design also. Okay? So you know the DNA gives rise to RNA, then the RNA translates into the protein, and the amino acid sequence present actually dictates that what will be the folding of the protein in 3D. So what will be the shape of the protein in 3D is decided by the primary sequence. And depending on the 3D shape, a drug has to be designed, because for one particular protein, depending on where there is some pockets in the 3D shape, your drug molecule, the pill that you will take, okay, the molecules in that pill will dissolve in your stomach, mix in your blood, will go to this particular protein site and find that particular pocket, and it will get itself attached, okay, through chemical bonding. And it also depends on the geometry. So that kind of things, that what are the normal shapes, what are the disease shapes, what drug molecules should have what property, what chemical, physical and geometrical property, so that they will have affinity and it will act. So that is designed solely by computer algorithms nowadays, and that is the subject of bioinformatics. Okay. Another interdisciplinary area is called quantum computing. That is a connection between computer science and quantum physics. So here the idea is, in normal computer you have zeros and ones, but due to quantum physics we can store any superposition of 0 and 1. Okay? So basically what we can do, suppose we have to search for patterns of say 0, 0, 0, 0 to say 1, 1, 1, 1. So there are say 16 possible patterns, all 4-bit sequence. So in classical computer I have to do operation 16 times, 1 on each. But in quantum computer, because here I can represent a state or a register, in classical computer one 4-bit register can contain one 4-bit sequence only at one point of time. So I need 16 many iterations. but a quantum register can contain a superposition of all the 16 states. And so therefore, I can do physical operation on that register so that I can find out the modified state corresponding to each of them also in a superpositions. Anyways, that is just one example. There are many other examples of quantum computing which I am not going to detail. Another interesting area of research is DNA computing, so where your DNA becomes the computer. Okay. So basically, this was proposed by Jadavpur. He was trying to solve a graph problem. You know the traveling salesman problem in graph. So basically, you are given any arbitrary graph, right? And you have to start from a city. The graph has so graph is nothing but say the collection of cities, and these are the roads or highways between the cities. Okay. So the job is you start from a node, you have to visit all the nodes and come back to this node without crossing one city twice. So you cannot come back in the same route, because that will optimize your travel. Okay, that is called traveling salesman problem. So if a company wants to send the salesman to 8 different cities, that is the optimization, right? You don't want that person to visit one city twice in the route. So whether there is a path and whether that path exists, or how to identify such a path, that problem can be independently solved in classical algorithm, in classical computer. There are graph theoretic algorithms to solve that. So the first DNA computer was designed to solve this problem in DNA. Basically, they represented each node by a specific DNA sequence. They represented each edge also by a specific DNA sequence. So the whole graph, which is nothing but a sequence of nodes and a sequence of edges, was represented by a bag of DNAs ultimately. Okay, and then there was some solutions put into it, some photonics, and ultimately you get output. And the patterns in the output DNAs after modification, they actually represent what are the roots or what are the subset of the edges that must be traveled in order to solve the problem. So that is DNA computing, and nowadays people are trying to use it to solve some other problems as well. And the beauty is that in 1 liter of fluid containing only 6 gram of DNA, that will have a memory capacity of 307 exabyte. So exabyte is 10 to the power 18, 1 inch, and a speed of 1000 petaflop. Okay? So it's more than gigaflop and more than teraflop. So giga, tera, and then beta, 10 to the power 15. Okay. Well, today most powerful computer does only a fraction of that. Another interdisciplinary area is computer science and music. You go into Google and you search, you will find there are many universities in the world. They are offering a dual degree in computer science and music. Okay? And computer science is used, so don't think that it is used to just generate the music. That okay, nowadays all the musics are actually edited in computers. You know, you have seen in studio, right? Post-processing. That is one aspect. Okay? But a more interesting aspect is, suppose you are given a music which is an analog signal, you want to classify it using computer algorithms. Okay? So again, digital signal processing also comes into play here, because you have an analog signal, the music, you have to represent it in a digital form, and that digital form will be a bunch of numbers, and you will apply your computer algorithm on that bunch of numbers to achieve your target. So one of my friends is working here in Jadavpur University, and recently she actually wrote a research paper on transforming the signals, the music signals, into a fractal domain. Okay? And if you look at the representation of the signals in that domain, then you can find stark difference in shape between different music of different moods. Okay? So for example, we know that certain ragas, so basically she worked on Indian classical music, and we know that some ragas invoke the emotion of pain. Some ragas invoke the emotion of, say, the crying. Okay? Some ragas invoke the emotion of happiness, but we do not know why. But by transforming the raw musical signal into another domain, and by looking at that domain, one can establish that you can classify these moods, that okay, which ragas or which compositions will favor which mood. Okay, so there is a mathematics involved in it. Oh, so in the music, they are basically, it becomes a multifractal map. In this particular example that I was sharing, so in one case the multifractal maps, they are separated like this, okay? In other case they are put close together. So this is one example of a binary classification, okay? So whether the music is of type A or type B, and this can be extended to multi-class classification. So I am in the last part of my talk. It's an infinite subject. I'm trying to finish it in finite time. So software engineering. In 5 minutes I will finish. So software engineering is a huge subject. One particular topic inside software engineering is reliability. Probably in your course, entire textbook of your software engineering will have only 3 to 5 pages on reliability. But if you go to research, this reliability itself is a huge domain. Okay? So I am just discussing one specific application of that reliability, which is from crowdsourced data. So crowdsourced data is an interesting type of data where you do not know the distribution of the data. So for example, suppose a software designer of some software, it may be an open source software, it may be a proprietary software, doesn't matter. But the developer or the designer of the software wants to know from the users of the software that what are the bugs that they are getting. Okay? So in the website, suppose the user can post bugs. Okay? So it's a pretty realistic scenario. Now, the problem is, and suppose there is classification. So whether the bug is a serious bug or a medium bug or a casual bug. Okay? So suppose there is scales between 1 to 5. Now the problem is, not all users who encounter the bugs will report the bug. Right? Some people may be lazy. Some people may be shy. Some people may have other priorities in life. Here, I will use some other software. So the thing is, so when you look at the data in the website, what you will see? You will see at time T1, I have found one report, and there the bug category is 5. At time T2, my next report comes, the bug category is 3. Time T3, another report comes, the bug category is say 4. Okay, and I have this sequence, and every element in this sequence is characterized by the arrival time, when it was reported, and what was the bug level. And the distribution is not known. You do not have any stochastic process to model the inter-arrival time, because not all users are reported. And also you cannot fit any natural distribution like Poisson distribution or normal distribution on the population also, because you do not know what was the population. It may be from different backgrounds, different areas, okay? And not everybody is reported. So that is called crowdsourced data, where no statistical modeling of the data can be done. The problem is, even without any statistical model of the source of the data, just by looking at the data, can we build some summary of the data or a function of the data to arrive at a single figure which is still mathematically meaningful to justify the reliability level of the software? So imagine now 2 different softwares, 2 different bug reporting forums, so 2 different data sets. Now you apply your algorithm on each of them, you arrive at a single figure from this algorithm as output, you arrive at a single figure from this data as output of your algorithm. Comparing by these 2 figures, you can say which software is more reliable, which one is less reliable, assuming they are on the same application domain. So that's a huge application. Recently one of my senior colleagues did this work in Indian Statistical Institute. Okay, so I know this stuff. Another interesting area is brain-computer interface. So, if you are bored, then your boredom will go away now. So you see there is a helmet put on the head of a person, okay, and there are probes. This is not invasive, okay, so this is on the surface, so you don't have to don't do it. The whole of the helmet, not separate. So it's like when you make ECG or EEG, right? You tap certain points of your body, right, to get signals. So here also it goes through the holes. Why? Basically the holes actually fixes the region. So if you insert something to catch, something to tap on that position of the brain. So these actually holes correspond to certain regions of the brain that you want signal precisely from that point. So you can insert different input probes in these points. You can get the EEG signal, and then you can do digital signal processing to map that EEG signal into computer understandable raw data. And from that raw data you can do unimaginable stuff. Suppose we are working with a paralyzed patient. The patient cannot speak, cannot move hands. Okay? So the patient needs to tell whether he or she is feeling hunger or feeling thirst. So if the patient cannot speak, there is no way to communicate. So the outside caretaker has to guess and feed or give water to the patient. But suppose with the help of this, actually we can make a system where even if the paralyzed patient cannot speak or cannot move eyes or cannot raise hands, can communicate to the outside world. How? It has been found. Actually, I have myself seen it. I have worked in New York State Department of Health in their brain-computer interface lab for a few months, and I've seen real patients, and this thing really works. So basically, from the EEG signal, you can do pattern recognition to identify what is the intent of the user. Okay? And the test has been done on a computer screen. Suppose a computer screen is there and there is a cursor, and the cursor can move either on the left and on the right. Okay? And you put the patient in front of the computer screen. There is no connection with the patient or this signal to the computer. This computer is completely detached from the patient or from these signals. So these signals are analyzed in a different way. What can be observed that by interpreting those signals, okay, so we can interpret whether the patient is actually trying to intend to move the cursor to the right or intending to move the cursor to the left. We can translate that, and accordingly we can achieve the task here. And how do you know it is correct? Because you can train the system on a healthy patient. A healthy person can really say that, okay, you are interpreting my EEG signal to be my intent of moving the cursor to the right, and you have moved the cursor to the right after analyzing my signal. But whether I really intended to the right, that person can tell. So you can test on healthy people, and after the testing is done, after the system is trained, parameters are tuned, you can apply on real patient and it will work. So this is the binary classification, whether left or right. You can do multiple signaling also. Right? So maybe you will classify whether I want to go to bathroom or whether I want to eat food or whether I want to drink a glass of water. 3-way classification. Or whether I want to sleep. 4-way classification. So this is very, very, very practical application. Involves digital signal processing, machine learning, and many other stuff. And this is the last example. Probably all of you have known it. Already know this. This is a TED talk by a 13-year-old girl. Her name is Trisha Prabhu. And see, user interface design or human-computer interaction is a specific area of computer science which tells you how to design the front end of a system. Where to put the text boxes, where to put the radio buttons, where to put the options, whether it will be drop-down manner or it will be a flat structure. what is the most user-friendly nature of a front-end design. That is the matter of research of human-computer interaction or user interface design. Now, this is an example of a particular problem of this area. So, she actually wanted to stop cyberbullying. You know what is cyberbullying? In Facebook or any other social media, often friends or peers, they bully each other, and sometimes it so happens that the bully is so strong that the victim can commit suicide. And she was moved by one such incident 2 years back when one little girl committed suicide, becoming victim of cybercrime, and then she tried to stop it. Normally what happens, if you are offended, you can block that person, right? You can complain to say the authority that remove the profile of that person. So these actions are already after the incident, right? Not before. What she wanted, that after the incident happens, the victim has already suffered. So, okay, it helps to some extent, but it is not of much help. A better system could be to stop the event from happening, right? So that's what. What she did, she did some research on human brain, and she found out that so our brain actually throws ideas or impulses, right? Let's do it, let's do that, let's go there. And the frontal cortex of the brain, the region there, gives you the rationality or the logic that whether to do it or not. So that helps you to think twice. And that area develops from the childhood, but the full maturity comes when you cross 18, when you are actually 25. Then the full maturity comes. So in teenagers, that area is not that much developed, and that is the reason why most of the teenage people, of course exceptions are there, but most of the teenage people, they act on impulses. They don't think twice. We say that think before acting, but mostly teenagers don't do it, and that is the biological reason for that. So what she decided, that for elderly people that think twice pop-up comes internally, but for teenage I will give the think twice pop-up externally. So she used some pattern recognition algorithm to identify or to classify, suppose you are typing a post, so before you hit the post button in your browser, there will be a program that will analyze what you are typing, and depending on the content, it will classify whether it is bully or not. And depending on that, before you hit the post button, it will give you a warning that wait a minute, think twice, your action may hurt someone. Okay? And of course, some people will be indifferent, but some people will respond. So it is better than not doing it. And when it was tested on real world data, it was found that 94% of the cases stopped. 94% of the people who were typing, they actually retracted. And 6% continued. And those persons will always be there anytime.
What I feel about this is, isn't there a chance that repeated use of this will atrophy the brain's ability to do the same think twice thing in real life?
That depends on your grooming, I believe.
This can be applied in the online world, but then
Yes.
bring it in the
No, I agree. Of course, every system has a limitation, but something is better than nothing. This is a starting point, and of course, people can think, oh, so a 13-year-old girl came up with this idea and implemented this system, and Google is adopting this system. Last year in Google's Innovative Research Forum, she was one of the finalists, her product, and Google has decided to adopt it in their browser, and probably other browsers will take it up. But more research.
He is 13-year-old.
Now 15. Okay? So, I want to end the talk with a quote from Donald Knuth. If you are studying computer science, and even if you are not studying computer science, because you are in this forum, you must know who is Donald Knuth. Okay? So, he is the author of The Art of Computer Programming. He is called the father of computer algorithms. So all the algorithmic analysis that we do, this algorithm is more efficient, this is less efficient, the time complexity and all that stuff is due to him. And also he is the inventor of LaTeX, an open source software for text editing. This presentation is prepared in LaTeX, open source software. That is due to Donald Knuth. So anyway, so he is a legendary figure in computer science. Got Turing Award, which is equivalent to the Nobel Award in computer science, 1974. So according to him, science is knowledge which we understand so well that we can teach it to a computer. So according to him, science is something which we can teach it to computer. If we cannot teach something to computer, that is not science. Okay? And if we don't fully understand something, so that we do not know how to teach it to computer, then that is not science, that is art. But it is not the end of the story. He also says that in this sense, we should continuously be striving to transform every art into a science. So those which we cannot make computer understand, that is not science, that is art, but we should not stop our endeavor. We should make computer understand, and in the process, we advance the art, even if we don't advance the science. So that ends my talk, and I welcome any question. I'll try to answer in my limited capacity. Please feel free to ask, and you are welcome to contact me later as well. My email is given.